Welcome to the cosmic frontier, fellow stargazers. Today, we're diving into a stellar mystery that's been baffling astronomers for years, but no more. Thanks to the incredible James Webb Space Telescope, JWST, we might finally have the answers we've been searching for. Stick around as we explore how the JWST may have cracked the case of the enigmatic puffy planets. The latest insights from the James Webb Space Telescope, JWST, reveal a compelling explanation for the unusual size of a nearby planet, shedding light on the mysteries of planetary evolution without resorting to complex theories. According to astronomers, the relatively low levels of methane in its atmosphere might be the reason why the planet, known as WASP 107b, appears so surprisingly inflated. Michael Line, a researcher in exoplanetary science at Arizona State University, elaborated on the findings. The data from Webb suggests that there's nothing extraordinary about the formation of planets like WASP 107b. It's not about having a tiny core or a massive gaseous shell, he explained. Imagine taking a planet similar to Neptune, filled with rock and less gas, crank up the heat, and suddenly it expands to resemble what we see today. Discovered in 2017 by the Wide-Angle Search for Planets, WASP Consortium, and situated in the constellation Virgo about 200 light-years away, WASP 107b is notably one of the lightest exoplanets discovered among the over 5,000 identified to date. Despite its size rivaling that of Jupiter, it has only about 12% of Jupiter's mass, roughly the mass of 30 Earths, compared to Jupiter's 318 Earth masses. This makes WASP 107b as fluffy as a microwaved marshmallow, the researchers describe. The peculiarities of WASP 107b, a planet whose expansive size and lightweight composition have puzzled astronomers, might finally be unraveling thanks to the latest data from the James Webb Space Telescope, JWST, complemented by earlier findings from the Hubble Space Telescope. Previously, the assumption was that WASP 107b had a small, rocky core surrounded by a thick blanket of hydrogen and helium gases. Yet this model didn't quite fit the planet's extremely low density, especially considering its proximity to its star, a mere 1/7 the distance between Mercury and our Sun, which still isn't close enough to justify such puffiness. David Singh of Johns Hopkins University, JHU in Maryland, who led one of the two recent investigations, shared a breakthrough. Our findings show that the methane levels in the atmosphere are only 1/1000th of what we'd expect, Singh explained. Since methane breaks down at high temperatures, its scarcity suggests intense mixing of gases from deep inside the planet with cooler layers above. This unexpected result indicates the planet's core is much hotter than previously believed. This additional heat may be due to WASP 107b's rapid orbit around its star, completing a circuit every 5.7 days in an elliptical path that subjects it to varying gravitational forces. This constant stretching and squeezing, similar to the tidal forces the Moon exerts on Earth, could be generating the extra heat that inflates the planet, much like heating a balloon. This dynamic insight helps clarify why WASP 107b is as voluminous as it is, resembling more a celestial marshmallow than a typical planet. Zafar Rustamkulov, a graduate student at Johns Hopkins University, JHU, and a co-author of one of the recent groundbreaking studies, revealed that the intense heat from WASP 107b's core, amplified by tidal forces from its star, is dramatically transforming the planet's atmospheric chemistry. According to Rustamkulov's statement from the university, this sweltering environment is not only depleting methane levels, but also increasing the production of carbon dioxide and carbon monoxide. The immense heat appears to be altering the chemical makeup of the gases within the planet, he explained, shedding light on a dynamic process that replaces methane with these heavier carbon compounds. In 2020, a breakthrough was made by a team of astronomers, including David Singh, when they detected helium in the atmosphere of WASP 107b. This marked the first confirmed detection of helium on an exoplanet, 2 years after its initial tentative sighting. The helium was observed as a sprawling cloud that extended far into space, hinting at the extraordinary reach of the planet's atmosphere. This expansive atmospheric halo allows ultraviolet radiation from its star to gradually erode the planet's atmosphere, stripping away about 0.1% to 4% of its atmospheric mass every billion years, leaving behind a comet-like tail. The planet's remarkably low density, likened to its puffy nature, provides astronomers with a unique opportunity to probe its atmospheric characteristics much more deeply than is possible with denser worlds like Jupiter. Indeed, recent observations by the James Webb Space Telescope, JWST, revealed an extraordinary phenomenon. It rains sand on WASP 107b, further underscoring the planet's unusual and dynamic atmospheric conditions. First, let's set the stage by understanding what puffy planets are. These are exoplanets with radii larger than expected for their mass, akin to a marshmallow expanding in the microwave. They defy the usual rules of planetary density, often being dubbed cotton candy planets due to their low density. We'll look at how their strange properties challenge our understanding of planetary science. Enter the JWST, humanity's most powerful space telescope, launched to uncover the universe's deepest secrets. With its advanced technology, the JWST can observe distant objects with unprecedented clarity and sensitivity. This segment explores the specific capabilities of the JWST that make it ideal for studying the atmospheric compositions and structures of these baffling planets. Recently, the JWST pointed its gaze at a well-known puffy planet, capturing detailed data about its atmosphere. This segment details these observations, highlighting the discovery of water vapor and unusual chemical signatures that suggest why these planets might be so inflated compared to their mass. What does this mean for our understanding of planetary systems? This part delves into the broader implications of the JWST's findings. We'll discuss how these insights could reshape our theories about planet formation and migration, especially in systems very different from our own solar system. Looking ahead, the JWST is set to observe more puffy planets. This final segment speculates on what future missions could uncover about these mysterious celestial bodies. With each observation, we edge closer to solving the puzzle of their existence and potentially discovering new types of planets. Unlike its predecessors, the Hubble and Spitzer space telescopes, the JWST offers a range of improvements in infrared sensitivity and resolution. This segment will compare how JWST's capabilities surpass earlier missions, enabling us to obtain better data about puffy planets' atmospheres and possible magnetic fields that may explain their bloated nature. Puffy planets might have extreme and dynamic weather systems due to their expanded atmospheres. This section will explore how JWST's ability to monitor atmospheric changes over time can give us insights into the daily and seasonal meteorological phenomena of these enigmatic planets. One theory about puffy planets is that they retain heat exceptionally well, causing them to expand. We'll delve into how the JWST's observations are helping to validate or challenge this theory by examining thermal emissions and heat distribution patterns in planetary atmospheres. Stellar radiation plays a significant role in shaping the atmospheres of planets. This segment discusses how JWST helps scientists study the interaction between stellar radiation and puffy planets, particularly focusing on how this interaction contributes to atmospheric loss or expansion. Do magnetic fields influence the puffiness of these planets? Here we explore the potential role of magnetic fields in protecting atmospheres from erosion by stellar winds, a factor that could contribute to the maintenance of a puffy appearance. Moons can provide critical clues about the history and composition of their parent planets. This part discusses ongoing efforts to detect moons around puffy planets using the JWST, which could further our understanding of these systems. Like moons, rings around planets can affect their characteristics, including atmospheric composition and density. We'll look at how the JWST might be used to discover and analyze rings around puffy planets, adding another layer to our comprehension of these complex worlds. The JWST employs advanced spectroscopy techniques to dissect the light from exoplanets, allowing us to deduce their atmospheric compositions. This segment explains these techniques and their importance in identifying the molecules present in puffy planet atmospheres. Gravitational interactions between puffy planets and other bodies in their systems, like other planets or stars, can also affect their structure and evolution. Here, we examine how JWST studies these interactions and their outcomes. Could oceans underlie some of the mysteries of puffy planets? This segment speculates on the presence of deep oceans and their potential effects on atmospheric density and composition, guided by data from the JWST. Atmospheric variability is a key aspect of understanding puffy planets. This part discusses how JWST's long-term observation campaigns are crucial for detecting and analyzing atmospheric changes that might not be evident from a single snapshot. Orbital eccentricity can influence a planet's temperature and atmospheric conditions. We explore how the JWST helps determine the orbits of puffy planets and the implications of these orbits for atmospheric dynamics and composition. Interstellar dust can affect the observations of distant planets. This segment explains how the JWST filters out the effects of interstellar dust to provide clearer views of puffy planets, enhancing our understanding of their true natures. While primarily studied for their unusual physical properties, puffy planets might also be targets in the search for life. We'll delve into how JWST's capabilities could help detect signs of life by examining atmospheric biosignatures. Finally, we discuss the importance of long-term monitoring of puffy planets by the JWST and future missions that could build on its discoveries. This segment looks forward to proposed missions that could further unravel the mysteries of these fascinating worlds. Although puffy planets may not be the most likely candidates for hosting life, it's important to consider their habitability potential. This segment discusses the criteria that make a planet potentially habitable and evaluates whether any puffy planets might meet these conditions, considering factors like temperature, atmosphere, and potential water presence. Understanding the chemical composition of puffy planets is crucial. We'll explore how JWST's instruments can identify various elements and compounds in these planets' atmospheres, shedding light on their formation processes and evolutionary histories. Planetary migration theories suggest that many exoplanets, including puffy ones, may have formed farther from their stars and migrated inward. This segment examines how JWST data supports these theories and what it reveals about the dynamic processes shaping planetary systems. Stellar ones can significantly impact a planet's atmosphere and structure. Here, we discuss how JWST observations help scientists understand the interaction between stellar winds and puffy planets, and how these interactions could contribute to their expanded atmospheres. By studying multiple puffy planets, astronomers can identify patterns and differences that provide broader insights. This segment highlights some key findings from comparative studies enabled by JWST, emphasizing what these comparisons teach us about the nature of puffy planets. Young planets offer a unique window into the early stages of planetary evolution. This part focuses on JWST's role in observing young puffy planets, providing clues about their formation and the factors influencing their growth and development. The core composition and structure of puffy planets are fundamental to understanding their overall characteristics. We'll delve into how JWST helps scientists infer details about planetary cores through gravitational and atmospheric data. Puffy planets may exhibit unique weather systems due to their large atmospheres. This segment explores how JWST's detailed observations can help detect and study weather patterns, such as storms and wind flows, on these distant worlds. Science often progresses through unexpected discoveries and anomalies. We'll look at some of the surprising findings JWST has made regarding puffy planets that challenge existing theories and open up new lines of inquiry. Collaboration between JWST and ground-based telescopes enhances our ability to study puffy planets. This part discusses how data from different observatories are combined to create a more comprehensive understanding of these planets' properties. How do puffy planets change over billions of years? This segment examines the long-term evolutionary processes affecting these planets, using JWST data to hypothesize about their past and future transformations. The age and type of a host star can influence the characteristics of its planets. Here, we discuss how JWST's observations of different star systems help scientists understand the role of stellar properties in shaping puffy planets. The techniques used to detect and study exoplanets have advanced significantly. This segment highlights how JWST's cutting-edge technology represents the latest leap forward in this field, particularly in the context of identifying and analyzing puffy planets. Public interest in space exploration is at an all-time high. This part focuses on how discoveries made by JWST, especially those concerning puffy planets, are being used to educate and engage the public about astronomy and the wonders of the universe. Technological innovations often arise from space missions. We'll explore how the advancements made in developing and operating the JWST are influencing other fields, from materials science to data analysis, and their broader impacts. JWST's discoveries are paving the way for future space missions. This segment discusses upcoming missions that will build on JWST's findings, aiming to further explore puffy planets and other intriguing celestial phenomena. Studying puffy planets requires collaboration across various scientific disciplines. We'll look at how JWST's data fosters interdisciplinary research, bringing together experts in planetary science, astrophysics, chemistry, and more to solve complex puzzles. Despite the progress made, many questions about puffy planets remain unanswered. This part highlights some of the key mysteries that JWST has yet to solve and what scientists hope to discover in the coming years. The exploration of exoplanets is a rapidly evolving field. Here we speculate on the future of exoplanet research, considering how JWST's contributions will influence upcoming discoveries and our understanding of planetary diversity. As we wrap up our deep dive into the world of puffy planets and the James Webb Space Telescope, this final segment reflects on the journey so far and what lies ahead. We'll summarize the key insights gained and the exciting potential for future exploration. One fascinating aspect of puffy planets is how their atmospheres escape into space. In this segment, we'll delve into how JWST observes these escape mechanisms, providing insights into the processes that cause a planet's atmosphere to expand and dissipate over time. Albedo, or the reflectivity of a planet's surface and atmosphere, can significantly impact its temperature and atmospheric properties. This part discusses how JWST measures the albedo of puffy planets and what these measurements tell us about their surface and cloud compositions. Orbital resonances, where planets influence each other's orbits, can affect a planet's characteristics. We'll explore how JWST studies these resonances in systems with puffy planets, shedding light on the gravitational interactions that shape these unique worlds. Clouds play a crucial role in a planet's climate and appearance. This segment examines how JWST's observations help characterize cloud formations on puffy planets, providing clues about their weather patterns and atmospheric dynamics. Transient events like flares and eclipses can offer unique opportunities to study puffy planets. Here, we'll discuss how JWST captures these fleeting moments and what they reveal about the behavior and properties of puffy planets. Dust can significantly impact the atmospheres of puffy planets, affecting their appearance and temperature. This part explores how JWST detects and analyzes dust in these atmospheres, contributing to our understanding of their composition and evolution. How do puffy planets evolve from their formation to their current state? This segment delves into the life cycle of these planets, using data from JWST to trace their developmental stages and the factors influencing their growth and expansion. Puffy planets often get compared to gas giants like Jupiter and Saturn. We'll explore the similarities and differences, focusing on how JWST's detailed observations help us understand what makes puffy planets unique compared to their more familiar counterparts. Magnetic fields can have profound effects on a planet's atmosphere and structure. This segment examines how JWST studies the magnetic fields of puffy planets and the role these fields play in maintaining their expanded atmospheres. JWST represents a significant advancement in infrared astronomy. This part explores how its infrared capabilities are particularly suited to studying puffy planets and what this means for the future of exoplanet research. Some puffy planets may have rings or debris surrounding them. We'll look at how JWST's observations can detect and analyze these features, providing additional clues about the planet's histories and environments. Stellar activity, such as flares and winds, can affect the atmospheres of puffy planets. This segment discusses how JWST helps scientists study the impact of stellar activity on these planets and what this reveals about their resilience and stability. Each new observation brings the potential for unexpected discoveries. Here, we highlight some of the most intriguing and mysterious findings JWST has made about puffy planets, prompting new questions and hypotheses. While primarily focused on physical characteristics, JWST also aids in the search for biosignatures. This segment explores how scientists use JWST to look for signs of life, such as specific molecules or atmospheric conditions, on puffy planets. The study of puffy planets is a global endeavor. We'll discuss how international collaboration in using JWST has enhanced our understanding of these planets, pooling resources and expertise from around the world. What lies beyond the JWST? Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.